So was that, okay. So what we'll cover is issues with survival data, and survival data is a little bit different. It's got a couple of quirky things about it that we don't see for other types of outcomes. I'll then briefly give you a tiny bit of theory. I just feel I should give you this theory about survival distributions and some of the important functions associated with them. Then we'll go on to the statistical analysis stuff. So I'll start with the relatively naive methods, whether they be descriptive, like Kaplan-Meier curves and things like medians. And then we'll start to go to formal analysis. And again, I will talk about naive methods first, like the log rank test. And then eventually we will go on to the models for survival data. So we'll talk about the all-important Cox proportional hazard regression. I'll run through a worked example of that. I will talk about the assumptions. Now, assumptions not something I've talked a lot about, but it's very, very important in survival analysis when you're using Cox regression, because it's got some assumptions that must be satisfied in order for Cox regression to be valid. Then I'm going to talk about some of the more advanced survival analysis models. Ideally, I would have split this lecture into two parts and talked about introduction to survival analysis, and then talked about some of the more weird and wonderful models like frailty models, competing risk models, and so on. As it stands, I'm just going to be able to comment on them briefly. But please, if you're interested in that, put in a request to the MARTA people for me to run a lecture on it, because I'd love to set up a really good lecture on advanced survival analysis methods. Okay, so let's talk about time to event data, or survival outcomes as they're generically called. Often we're interested in an outcome involving how long until an event occurs. So for example, in clinical research, this might be time to death, which is that's where survival analysis gets its name. But it could also be time to remission after some sort of treatment. It could be length of stay, say in an ICU or a hospital, and that's also a very common time to event outcome. But it also could be time to recidivism if we're talking about addiction treatment, and so on. So all of these endpoints come under the heading of survival outcomes, even though death is not the endpoint that we're interested in a lot of cases. So most survival analysis, I should mention, are generally performed in clinical settings. You tend not to see survival analysis too much in population health. And there's a very good reason for that, because hospital data is, there's sufficient, the word is vigilance with survival, with hospital data, where we will have time of diagnosis or time where risk starts to the point where a disease or endpoint occurs. When we have population-based studies, particularly retrospective data, we just don't have that information to be able to calculate these time to event outcomes. So I think that's one of the reasons they're much more common in clinical studies than population health, among other reasons that you could, no doubt, think about. The only other common application to this is the survival of products. So for example, horrible corporate international companies will calculate the median or average time for say a computer failure or a phone failure, and then they will sell you overpriced warranties based on these sorts of things, but they price them based on survival analyses. Okay, so what is it that is weird about survival data? It presents a few problems that we don't see elsewhere, specifically data truncation and censoring, and I'll go into a little bit more detail about that soon, but also conditional probability. So to consider the probability that a subject might die at a particular point in time, we have to account for the fact that they have survived up to that point. In other words, the probability of subject X dying on day 30 is conditional on them being alive on all of the preceding days. And I know that sounds a little bit strange and almost obvious, but it has implications. And I guess the easiest place to see where this comes into effect is when we calculate Kaplan-Meier curves. And I'll show you what I mean later on with that. So this is a bit of a strange aspect of survival data. So what this really means in the end, these first two issues, is that unlike any other type of outcome that we consider in clinical studies, is that a survival outcome has two components. First, a continuous variable, usually continuous, which is represented by time, how long, and a binary variable, which tells us whether the event happened or not, which is sometimes called a failure variable, and that would be, did someone die or not? Because in a lot of studies, the study ends and there are people still alive, okay? And that would be censored data. So again, as I said, I'll go back into this, but just remember, survival outcomes are a little bit strange in that respect. They've got the two components to them. How long and did it happen? Okay, so here's an example of 6 patients that are enrolled into a study. And just remember with these sorts of cohort studies, that patients are usually not all enrolled at the same time. They can be, but often it's basically as they walk through the door or whatever, they are enrolled in the study. Okay, so here we have 6 patients, A, B, C, D, E, and F, and different things happen to them. So first of all, we note with patient E, who was enrolled into the study at about week 4, I think that's right, might be week 3, that they were lost to follow-up at around week 10, okay? So in our time we observed them, the event did not occur, and then we lost them. Similarly, patient C also started around, what's that? I think that is week 3, and then they withdrew after 3.5 weeks. They withdrew themselves from the study. They weren't lost to follow up, they chose to exclude themselves. And we've got to be very careful between these two types of events, that they may or may not occur at random. So particular types of people might be lost or might withdraw themselves, and that represents a type of bias. And a lot of the time we just assume that loss to follow-up happens on a random basis. Okay, for patient, sorry, did I even list them? Which one am I talking about here? I think I must have taken the letter off them. Where are they? I'm looking at it. Or maybe they've been truncated. I don't know. But I guess here, if we have an outcome of disease-free survival, as opposed to all-cause mortality, we've got to be careful that when a patient dies, so they do meet the endpoint of dying, that it is actually due to the disease. Otherwise, they are also censored from the data. It's just like being lost to follow-up or withdrawing. Okay, so now let's talk about censoring. Here, patients B and D got to the end of the study but did not experience the event of interest, which might be something like death from myocardial infarction, for example. Okay, so they both survived. At this point, they became censored because we don't know what happened to them after the study died. But also patients C and E are also right censored, so censored at the right end, because we also didn't know what happened to them after they were either lost to follow-up or withdrew from the study. So those 4 patients are all what are called right censored. They are cut off on the right end of the number line. Okay, we also note that patients A and B are what's called left truncated. What that means is there was time at risk of death before they even entered the study. So presumably patients C, D, E, and F were only diagnosed with the disease halfway through the study or enrolled in the study and they were disease-free. But patients A and B may have actually been at risk before the study happened, and we don't know how long that was. So we call that left truncated. I guess that's something I don't want to go into a lot of detail. The most important one we're going to talk about today is the right censoring. And this is what survival analysis is very good at doing. Otherwise, we could just use a logistic regression and say, did they die by week 10 or something like that? Okay, so survival data has these strange properties about it, and lots of things can go wrong. And the most common are first, right censoring. The second most common is left truncation. Now, right truncation and left censoring also occur, but they're a lot more unusual. Okay. So now let's talk about some very useful distributions and functions that arise in survival analysis. The first I'd like to talk about is the probability. Hi, I've got a customer now. I'm happy. I don't feel so weird. Okay, so first we'll consider the probability distribution or density function, FT, and the cumulative probability distribution function, capital F of T, of survival time. Okay, so FT represents the probability of dying on a particular day, day 30. Now remember, you can for example, day 23. Now remember, you can only die on day 23 if you were alive on day 22. This does not take this into account. However, when we consider the cumulative distribution, which represents the probability of dying any time up to a particular day, T, right, that does actually take that into account. Now, the thing is we do not directly use these distributions. We use what's called survival function, which is very closely related to one of the, well, actually, in some respects, both of these distributions. Because really, capital F of T is just the cumulative version of small f of t. Okay, so what is this survival function? How is it calculated? And I figured this is the first time I've thrown a bit of calculus up. So you've gotten away scot-free up until this point, and I don't expect you to understand this, except to note that we consider the area under a distribution curve for a cumulative distribution. That's where it gets its capital from. And so the survival function literally represents the complement of 1 minus this cumulative distribution. Now, by the way, this cumulative distribution is often called cumulative incidence, and I'll come back to that right at the end when we talk about competing risk models, okay? But really, what does this represent? The survival function, capital S of T, is the probability of surviving longer than a particular time, where capital F of T is the probability of dying within a particular time. So dying before and including day 23. So S of T, the corresponding S of T would be 1 minus that probability, which is the probability of surviving longer than 23 days, okay? That's the important thing to remember. Do you need to remember this integral function? No, you don't. No, you don't. The other thing that's very important to us is the hazard function, small h of t, which is the instantaneous risk of an event at time t. So the chance of dying at a particular time. So the hazard function is the probability that if you survive to day t, you will die in the next instant. Okay, so it does take that survival up to a point into account. Okay, now, sorry, I know this is probably not a nice definition, but I did want to give you a formal definition, and then we'll consider these in a much more practical sense. I have tried to avoid theory, but I think these are actually important things to come back to. Okay, if you just want to think hard about it and you're serious about your survival analysis. Okay, So now let's get on to the much more practical side of survival data, which is its analysis, okay? So like all other types of analysis, survival analysis can be used to generate descriptive statistics, including graphs, some classical bivariate methods, specifically survival times in terms of a single categorical variable. Is the survival experience for males the same as the survival experience for females, for example? And number three, and this is much more useful, particularly if we're talking about observational cohorts, we need multivariable models. And the most commonly used method by far is proportional hazards regression, also known as Cox regression, also known as Cox proportional hazard regression. Now, I would probably remember that last name, Cox proportional hazards regression, because the notion of proportional hazards is so very important to whether it works or not. And I'm going to explain very clearly what proportional hazards actually means soon when we get to it. Okay, so let's now first talk about a graph. And everybody's probably heard of this graph. So remember, we're just here at descriptive statistics. This graph is called the Kaplan-Meier survival curve. Okay, and what is it? It is actually a statistic. It represents an estimator of the true survival curve. So the Kaplan-Meier curve is often represented as S of t with a little hat above the S, because it's an estimate of the true survival curve of the population. It's also known as the product limit formula for a very sensible reason. A very sensible reason, and you'll see that on the next slide. By the way, I don't think I know anyone who calls it the product limit formula, but it is a very sensible name for it. Now, a couple of things to note about Kaplan-Meier curves is they are purely empirical. They are calculated 100% off the data we have in hand, okay? And for that reason, they are non-parametric. We make no distributional assumptions about survival time, whatever. So like when we have continuous outcomes, we often assume normality. This is not the case here. We make no assumptions about the distribution of survival times when we're using the Kaplan-Meier curve. It's very useful because it accounts for censoring, for right censoring in the data, and it generates, if you've ever seen one, it generates that characteristic stair-step survival curve, okay? So it looks like some downwards facing stairs. By itself, it does not account for confounding or effect modification by other covariates. And contrary to popular belief, and I would like to underline this point, Kaplan-Meier curves are not a test. They are just a picture. They are a graph. The reason I say that, and I warn you about it, is because I hear people say all the time, we conducted a Kaplan-Meier test. Now, this is probably because software like SPSS will put a p-value on the Kaplan-Meier plot, which is not from the Kaplan-Meier plot, but from another test. So people think that the Kaplan-Meier itself is a test. No, it's not. It's just a graph, okay? So it's a descriptive statistic. Okay, so here's where Kaplan-Meier curves gets its name, and also here is where we can see this notion of conditional probability. The chance that I die on day 30 depends on the fact that I've survived the first 29 days. Okay, so here we have 5 patients, okay, and some of them died. In fact, 4 of the 5 patients actually died, but one of them did not die. Okay, so this patient was censored. I should probably switch that the other way around and make that 0, 0, 0, 0, 1, or really just call that failure rather than censored. In other words, these 4 patients died, this one did not. The study ended before they died, so they are censored. Okay, so we see our first patient, the first patient to die is patient 1, and they died on day 6. So what this really means is from day 1 to 6, 5 out of the 5 patients survived. So the probability of surviving up to but not including day 6 is 100%. There it is, okay? Now we then see a patient dies on day 6 and the next patient does not die until day 14. So in that interval, day 6, including day 6, up to day 14, but not including day 14, so exclusive, that one patient died. So the probability of surviving up to but not including day 14 is 80%, because you've got a 100% chance of surviving the first 6 days, there it is, and an 80% chance of dying between day 6 and day 14. So the survival curve at that point goes from 1 down to 0.8. And so on. Now you can see what will happen is people are now leaving the study, they're dying. So the probability of dying in the interval 14 to 21, where are we? Is, have I got this right? Here, yeah, sorry. From 14 to 21, something else occurs. Actually, I just got to check I've got this right. Yeah, between day and 14 and 21 is 0.6 because another person dies. Actually, I might have switched this around. I better just check my notes here. Because day 21, that person is not dying, they're leaving the study. So that should actually be, 0.8 there. Sorry, that's a typo on my study, because this person left the study at day 21, but there was not a death event. Okay? Sorry, that's a mistake. I'll fix those and actually change it. But basically, we get this idea of dying in a particular interval depends on surviving the previous intervals. Then, essentially, all we do is plot that on our x-axis and that on our y-axis, and that is the Kaplan-Meier curve. Now, we don't do this by hand. We have software to do it for us. So here is the resulting Kaplan-Meier function. From day 0 to 6, you had a 100% chance of surviving. Then it went down to 0.8 between day 6 and 14. 14 to 21, it actually stayed at 0.6 and then continued because this person here is censored and so on. Okay, so here's this characteristic step stair shape of it. All right? Okay, so now for the rest of the lecture, or most of the rest of the lecture, I'm actually going to refer to a particular data set. This is an extremely famous study. I think they published oodles of papers out of the study, and it's the Worcester heart attack study, which basically followed up and was about the long-term survival following a myocardial infarction among residents of Worcester in Massachusetts. And what we're going to do is consider a very trimmed down version of the data set. We'll consider only a small selection of covariates, which will have both continuous and categorical predictors in there, and only a small subset of patients, about 500, but there were thousands and thousands of people in this study, and it's a very famous study from quite a while back now. In fact, it's probably still going. It's one of those rolling cohort studies. Okay, so here are a bunch of covariates. We're not going to consider all of these, but up until this yellow point here, these are the covariates, the predictors, and then after that, we have the time to event outcomes. In fact, with survival data, we have to often calculate them ourselves. So we will have an admission date, we'll have a discharge date, and then we will calculate, say, the length of stay, which is discharge date minus admission date, and what their status was when they were discharged. So alive or dead. So here are the two components for the length of stay variable. How long did they stay? Were they censored, or did they fail or die? That's one time to event outcome. But here we also have another time to event outcome, which is a total length of follow-up because these people were followed after they were discharged from hospital as well. So here we have C, which was their last follow-up date minus their admission date, and whether they were alive or dead at the last follow-up. So we could analyze either this one or this one. But just note, with both of these survival outcomes, there are two components. How long and did it happen? Okay. So here is our Kaplan-Meier curve for this data. And you can see, you can probably guess that this is actually total follow-up time because patients tend not to stay in hospitals for 2,300 days. It's just too long of a follow-up. But you can see here, with something like myocardial infarction, there's a quick drop-off in the first 30 or 40 days after you've had the initial myocardial infarction. So if you're going to die, you're going to probably die quickly. But after that, you can see quite a slow decrease in the survival function. Okay, and by the way, this is all-cause mortality. It's not necessarily disease-free survival we're considering. So these people here might have died from a totally different disease, or a disease that might have caused the myocardial infarction, but might have caused some other problem with them too, okay? So it might have been diabetes, and it might have been another diabetes complication that killed them. Okay, so that would be our Kaplan-Meier curve that we would get from this data. And you can see it's much smoother because we have a lot more patients, okay? The reason it does this at the end and it starts to get much, I see the resolution becomes much grainier at the end here, is people are dropping out of the study due to loss to follow-up, but then you've got the occasional patient who dies here. So you might find by the time there were only 5 or 6 patients left in the study, one of them might have died. So they had a very profound effect on the Kaplan-Meier curve. What is the upshot of here? Don't really trust the end parts of a Kaplan-Meier curve because they're based on very few patients as a general rule. Okay, so how do we read this graph? How can we actually use it, this Kaplan-Meier curve? There are a lot of things. It actually yields a lot of information to us. So often a clinician might want to know or a patient for that matter, might want to know what is the survival time that 50% of individuals can expect to survive. Now, reading this off a Kaplan-Meier curve, we find the 0.5 mark on cumulative survival. We go across, boom, there it is right there, and then we look down. That is the survival time associated with 50% of patients surviving. So we can see about 50% of patients survived 1,600 days. Okay? It's probably, I mean, that's a nice way of just looking at it, but we don't need to do that, and that's rather inexact. We can usually just get our software to spit out median survival time for us. Okay? But the point is we could work out the survival time of 75% of patients and 25% of patients, which would be all the way over here, and so on. Okay? And that's really how we read that graph. Okay, now I'm mentioning median here. Why wouldn't we consider the mean survival time? The fact is survival times are bound by 0 at one end. You can't survive a negative amount of time. So they tend to be right skewed data. So they're bound on the left, so they tend to be right skewed. There's a long tail out on the right. So we would expect these survival times to be positively skewed. So we really want to use a median rather than a mean. There are some special means that are used with survival time. I don't use them that often. I'm not saying they're bad. There's one called the extended mean. There's one called the restricted mean. But most people will really just use the median survival time. And we can see here that the median was 1,627 days, which is about what I guessed it would be looking at the Kaplan-Meier curves. And a lot of the time, these are routinely output with Kaplan-Meier curves anyway. Okay, so here I can not only calculate the median, but I can get the 25 percentile and the 75 percentile. Now remember, this was when 25% of people were still alive, 75% of them had died. So we can see that's going to be obviously a longer amount of time than the median. So by the 25% of patients were still alive on day 2,353, but 75% were still alive on day 295, and so on. Okay? Okay, so now basically that's really nice. If we just want to describe a single cohort of patients, we could just use the Kaplan-Meier curve, a single Kaplan-Meier curve by itself, generate some summary stats like the medians and so on. But a lot of the time we're much more interested in comparing groups of patients, or at least bringing a predictor or a prognostic variable into our model. Okay, so we need tests. We need basically tools that can tell us, is something an important prognostic factor or risk factor or not? Did our treatment work? And so on, okay? So there are a number of tests that exist able to compare survival curves from different groups. So, and as I said, survival time for those on treatment A versus those on treatment B. The bivariate test we're going to consider, and it's probably the most common classical bivariate test used, is a non-parametric test, and it's called the log rank test. Now, I'll just remind you what non-parametric actually means. It doesn't mean non-normal. A lot of people think that non-parametric tests mean the data aren't normal. What non-parametric means is the data aren't from any particular distribution we know and are using in our model. Okay? So a logistic regression is a parametric test, but it does not assume normality of all. Of course not. Our outcome is a binary variable, but it is still parametric. A Poisson regression is parametric, okay? Because they assume a particular a theoretical underlying distribution. A non-parametric test, probably a better name for them, is distribution-free tests. Okay, so the first thing we would do if we're comparing groups is use our eyes, and here we can visualize group differences by generating group-specific Kaplan-Meier curves. Okay, again, I remind you this is not a test, it is a graph. However, when we look at the graphs, we can see that males, which are the gender 0, the blue curve here, appear to have a better survival experience than females who are represented as red. Okay, so in other words, let's look at the median. We can see the median survival time for females, where is it about here, is only about, sorry, I'm finding it hard to read that off, around 1,250 days, I'm guessing. There it is, there's the line around there, where for males, it's over 2,000 days. There it is there. Okay, so straight away, I mean, that seems to be a considerably better survival experience for males. Note that I'm not formally testing here, I'm saying appear to be, or in the sample that is true. I don't know if it's necessarily true in the population. Okay, that's what testing is for, to make statements about the populations based on our sample. Okay, so let's look at the descriptive stats. I'm just going to look here at the median. I won't worry about the other ones. But as I said, the males, it was about 2,160 is the median survival time for males, but it was only about 1,317 for females, okay? Now, just a couple of questions here. Why is there no estimate of the 25% survival time, or 75% of people dead for males? Simple. the curve never got to that point for males. So we can't estimate the point at which 25% of males survived. It never crossed this little grey line here. Okay. The second question is why there's no standard error for the median survival time for males. Why is this blank? The simple answer is there was actually only one male patient left in the cohort when it crossed the 50% mark, and we cannot calculate standard deviation when we've only got a single patient. Okay, so that's just, I guess, more of a curiosity as we're going past. Okay, so now let's do our magic. Just like the chi-square, when I was talking about this last week, the log rank test is a bit of a magic test. It gives you a magic number and we can say, yes, there was a significant difference in the survival experience between males and females. But the statistic itself, the chi-square statistic, doesn't tell us anything, really. It doesn't tell us anything except that there is a statistical difference between the two groups. It's a yes-no answer, and it's only by looking at the Kaplan-Meier curve and at the summary stats that we actually know which set of patients have the better prognosis, okay? And this is, again, this is one of the real flaws of these classical bivariate tests, whether it be in survival data or categorical outcomes or whatever, it doesn't really matter. These magic statistics that, well, they're not magic. I mean, they do actually have some theoretical basis, but it's just not something that's intuitive to your, I guess, your normal person, all right? Okay, there's one other comment I will make, and I will come back to this a couple of times, about Kaplan-Meier curves and making statements about differences between groups. One thing we assume when we do a Kaplan-Meier curve, when we do a log rank test, and later on when we do Cox regression, is that when we say life appears better for males, in this case, than for females, or the survival experience is better, we assume that it doesn't matter where in the survival experience we're talking, it's always better. So whether it be at the start or at the end, the blue line is always above the red line. What about when they cross over? Like this. So here we can see, and now I've gone to red to purple, sorry, I've been a bit inconsistent here. We can see here for the first 130 days, and this has nothing to do with the Worcester data, it's just an example, for the first 130 days that the red group had the better survival experience and the purple group had the worst survival experience, but after that day 140 or whatever it is, they switched around. Now, can I say reds have a better survival experience than purples? No, I can't. It depends on where in the survival experience this happens, okay? So we have to be very careful, particularly in clinical trials, when we actually say a treatment works, because we need it to work better in one group than the other. Sorry, we need the treatment group to have a better survival experience throughout the whole survival experience in order to be able to conclude that, okay? Now, just as we're going past here, I want to say that this is a case of severe disproportionality. And I'll come back to this notion of proportionality better, but this is bad. In other words, if I see this, my log rank test or my Cox regression are not valid at all, okay? Because both of those tests make the assumption that one group's always better than the other. Okay, so now let's talk about these true models, this Cox proportional hazard regression. So the advantage of this model, and all models actually as a general rule, is we can consider multiple variables. Those variables can be categorical and or continuous. And the model we're going to use to do it, very common model in survival analysis, is Cox proportional hazards regression. A lot of people just call it Cox regression, and that's fine. It's just, I'm going to call it this today because this notion of proportional hazards is so important. But you'll also see that Cox regression is much more useful method than, say, the log rank test. But it also makes a couple of very important assumptions too, okay? And these assumptions need to be valid for Cox regression to work. Okay, so Cox proportional hazard regression is most widely used method for modelling time to event data. Log rank test is very common too, but that's not modelling. That's a classical bivariate test. Cox proportional hazard regression is an example of a semi-parametric method. Okay, now why is it semi-parametric? First, it makes no assumptions about the form of the survival distribution. So it is distribution free, okay? However, it's also not fully non-parametric, as it does make assumptions about the functional relationship between the covariates and survival. In other words, it's got a linear model type of side to it. So it's sort of half parametric, okay? Now that's probably not, and I know they call it semi-parametric, it's probably not the best choice of words to call it semi-parametric, but let's just say it's formal, unlike non-parametric tests, but it's still distribution free, like non-parametric tests, okay? How does it manage to be sort of parametric and sort of non-parametric? Because it makes an assumption about proportionality. And again, I'm going to talk in a lot of detail about this assumption because it's so important for this method. Okay, so here it is. And again, I have tried to avoid in this lecture series, I've tried to avoid showing you too much mathematics, but I think it's very important here that you actually understand how this model works. What we are trying to model here is the hazard. Okay, the hazard for patient number I, okay, can be based on a hazard distribution, okay, distribution of deaths that is shared by everybody, okay? So we assume that everybody has the same underlying survival distribution except what can be explained by what type of patient they are. That could be gender, age, BMI, whatever. So in other words, any difference in someone's probability of dying can be explained by the model. And beyond that, everybody shares the same underlying hazard distribution. That's what this statement actually says. We can also see that there's an exponentiation of this regression-like model here. And what that really means is that this is a log linear relationship. In other words, the log of the hazard can be modeled in something that looks very much like a linear regression. Okay, so there's a log linear relationship between the hazard and the covariates. All right? And by the way, you may not care about that, but it actually makes it very nice. It makes things work out very nicely. Okay, so the form of the model that I have given you here, which is the simplest form a Cox regression can take, the first thing I want to point out is that the covariates in this model are time independent. So they're often, another name for time independent covariates is baseline covariates. So these are variables measured at baseline and we don't measure them again. We assume they stay constant throughout the study. So in other words, note that there is no t component to this x beta up here. So looking at see there's no t's in there whatsoever. Okay, so time is assumed not to come in to the covariate outcome relationship. So just to explain what baseline covariates generally are, is they're typically represented like variables by age, sex, things that don't change throughout the study. Now, technically speaking, you can say, well, age changes throughout the study, but it changes at the same rate for everybody. So 1 year later, everybody's going to be 1 year older. we don't need to consider it a time-varying covariate. It's a baseline covariate. To give some examples of some time-varying covariates, it might be systolic blood pressure or diastolic blood pressure, where someone's blood pressure can change over the course of the study, and this might actually change their survival or whatever the outcome is. Okay? We're not going to go into models, Cox models, that actually consider these types of variables, but I do mention them briefly at the end when we talk about advanced models. Okay, so the parameters are estimated in this Cox regression. The beta can be transformed to obtain the hazard ratio. Now, I'll explain a hazard ratio in quite a bit of detail. So as with logistic regression and Poisson regression and the log linear type models, beta hat can be exponentiated to get this hazard ratio. In other words, if our software spits out betas, we just exponentiate that beta and we get the hazard ratio. Often we don't need to do that. The software will do it for us. If you use R, you actually R will even do it for you automatically too. Even though R doesn't with a lot of its other generalized linear models, it won't do that. So by the way, I should be careful saying that Cox regression is not a generalized linear model. It's closely related, but it's not actually a generalized linear model like logistic regression. So what are hazard ratios? They represent the risk of the event, let's say death. So the risk of death for one group relative to the other, if we're talking about a categorical covariate, or the change in hazard as we increase a unit if we're talking about continuous covariates. And I will give you examples of both of these soon. So let's just consider a very simple example. We're going to consider a bivariate model, a single predictor, gender, which is dummy coded to be 0 for males and 1 for females. Okay, so there's our model there. And I just want to show you how to interpret it, and a clever, simple little trick that Cox regression uses to get around, to make it sort of semi-parametric. And maybe you don't think it's clever. I think it's very clever. Okay, so here it is. We perform, just say, for example, our Cox proportional hazard regression, a bivariate one, and we found that our beta gender equals 2. So we could get a model for our males and our females. So the model for our males would be the baseline hazard times e to the 2 times 0. And remember, 0 is the dummy code for males, which equals h0 of t. In other words, anything raised to the power of 0 is 1. So that works out to be ht. For females, it is h0 of t, e to the 2 times 1, because females were dummy coded as 1, which equals h0 of t times e to the 2. So the hazard ratio of females relative to males would be this over this. Now, here's the clever bit, and I'm not sure if whether you actually spot this. This is how Cox regression gets around this non-parametric, this distribution-free assumption. It says as long as people have the same underlying hazard distribution, except for whether they're male or female in this case, then these just cancel out. It doesn't matter what they are. They could be apples. Do you know what I mean? But they cancel out. And that's Cox's very tricky way around dealing with this hazard function. We don't care what it is as long as it's the same for males and females, except for the male and female effect, if that makes any sense. So anyway, they cancel out. We get an e to the power of 2, which equals 7.4. So how do we interpret that? This means mortality in females is 7.4 times more likely compared to that of males. Sorry, typo there. Okay, so that's a very clever little trick being used there. And I don't know, maybe people won't think that's clever. I've always thought it was just a great way to sneak around parametric assumptions. Okay, so remember, I just want to go back because I do want to underline this point. that the assumption here is that any differences in survival between, say, males and females can be explained by this part of the model, and that once you take out the male and female difference, everybody's the same. They share the same hazard, baseline hazard distribution. Okay, now the reason that is so important is that's called proportionality. Okay, so just to recall our data, let's do this in a real data set. Here they are here, and remember, I think we look at length of stay. I think from memory now, I talk about length of stay from now on, and we are just going to consider two variables. The first being the type of myocardial infarction, whether it was a non-Q wave or a Q wave myocardial infarction. And this is a binary variable, and it represents our study effect. That's our research question. Do patients with a Q wave have a considerably worse prognosis than people, have a better prognosis than people with non-Q wave? And we know they generally do. A variable we think that might interfere with this research question as a confounder is BMI. So we're also going to account for that. Now, the fact is in real life, there would be lots of confounders, but I really did want to keep things simple here. Okay? How am I going to go about this modeling? I'm going to do each of them separately first to give us unadjusted effects, also known as crude effects, and then I'm going to put them both into the same model. Okay, so let's do that. So now, this was a mistake of mine. I used SPSS here. And you should really never use SPSS at all. By the way, they're going to sue me if they ever hear one of my lectures, but I've just had so many problems with it. I've taught it to a lot of people, and it appears easy. And my conclusion would be, is it's easy to do the wrong analysis in SPSS. Now here, let me give you an example. I dummy coded myself non-Q wave to be 0 and Q wave to be 1. Now SPSS said, no, Cameron, you're an idiot. Really? I'm going to switch it around on you, okay? So I don't care that you called one 0 and the other 1. I'm going to switch them around. Now, I did not ask it to do that. It just did it by its own choice, and I can't stand that, okay? So I'm going to mention, if I haven't mentioned it before, I hate SPSS, and I'm going on the record to say that. Obviously this is a recorded lecture. I find it very difficult, and I've seen a lot of people make mistakes with SPSS, more so than any other software. So in other words, it switched my referent without my permission. I'm just glad I spotted it, because I might have had novel but incorrect results otherwise. Okay, so first of all, my first model, I'm going to look at the myocardial infarction type, whether it was Q wave or not, and just remembering that Q wave is now the referent and non-Q wave is the group we're comparing, okay? So here we get our beta. Now I could exponentiate that myself, but you can see SPSS has done this for me. It's exponentiated. It doesn't call it hazard ratio. It calls it exponential of beta. And it's also given me a confidence interval for it and a significance level. Okay, so let's go through this and see what we can say from our results here. Significance test of beta is a Wald test. It gives P is less than 0.05, implying there is a difference in the hazard between those who have a Q wave and a non-Q wave myocardial infarction. Equivalently, we could test that same hypothesis using the hazard ratio itself and saying that 1 does not occur in that confidence interval. In other words, a hazard ratio of 1, no differential risk, is not a feasible statement given our data. That's how we would interpret a confidence interval. We can rule hazard ratio of 1 out, okay, because it does not occur in the confidence interval, not even close, okay? So how would I interpret this hazard ratio? Those with non-Q wave MI have almost 2 times the chance of dying relative to those with a Q wave MI. Or, equivalently, we could say non-Q wave MI have a 93.5% higher chance of dying relative to those with non-Q wave. Now, that second form I find much more useful if a hazard ratio is less than 1. If it's greater than 1, I prefer this way of saying it. Okay, now let me give you an example of what I'm talking about here, because BMI actually seems to be protective. I should say higher BMI seems to be protective. So here's the BMI model. There's our beta. There's our exponential of beta. Okay, and just be careful here that sometimes the scale of continuous variables is arbitrary. So a hazard ratio close to 1 does not mean something is not a profound effect. Let me give you an example. Age can be measured in how many days old you are, how many months old you are, how many years old you are, and how many decades old you are. All of those will have the same p-value, but they're going to have different hazard ratios. We would expect a hazard ratio for how many days older I am to be much lower than how many decades older I am. So just be careful of the scale of a continuous variable and its hazard ratio. Just because it's close to 1 does not mean it's trivial. It's a trivial effect. As in this case here, 1 unit of BMI is not a huge step, is it? Okay. So my hazard ratio is 0.91 or thereabouts, and there's my confidence interval. And how would we interpret this? As we go up 1 unit of BMI, the chance of death reduces by 9.5%, 9.4%. Okay? That's quite a strong effect. Okay? It's also a bit weird too, because you would think BMI would be a risk factor. Higher BMI would be a risk factor. It wouldn't be protective. But you've got to remember, this is recurrent myocardial infarction. It's not an initial myocardial infarction. So this is someone who's already had one. All right? So you just remember that when interpreting this, but because this is real data. Okay. So now let's consider a multivariable model. Let's consider both of our covariates at once. Now, remembering MI type, the type of myocardial infarction, is our study effect. It's our effect of interest. And BMI is a potential confounder. We're not actually that interested in BMI. We probably just want to adjust for it. Okay? Now, how am I going to decide it's a confounder? And I have briefly mentioned this in previous lectures. The way we generally do it is we note that when we add BMI to the model, does it substantially change the MI effect? So we could set that, say, as a change of 10% or a change of 20%. I tend to vary it depending on what type of study it is. Okay, so for example, if it's an exploratory study, I might be a lot more, it might need to be much higher. But in a study like this where I have a particular study effect, I might be a little bit more rigorous with it. Okay, so basically, here it is. If the beta or the hazard ratio, now remember it's not exactly the same, but if my beta changes by 10% when I add BMI to the model, then BMI is a confounder. If adding BMI to the model has no effect on the MI effect, then it's not a confounder, all right? So just to remember, our crude or unadjusted beta for MI type was 0.66. So if that changes by more than 10% when we add BMI to the model, then BMI is a confounder. So doing that, I'll go straight there and I'll come back to this in a minute. Okay, so we see that in our crude model, we had 0.66. Now we've added BMI to the model, we get 0.589. Okay, so there's been some change. How large is this change? We just basically, we see it's over a 10% change. What that means is BMI is a confounder, so we should add it to the model, okay? We need to adjust for it. In other words, this is not a good representation of the relationship between MI and survival. This is a much better one. That's what it's saying. All right? Okay, so that's the first thing. Should BMI enter the model? Because it's a confounder. Another reason it might enter the model is it just might be an independent risk factor itself. It might be a significant risk factor. In this case, it's actually both. It's a risk factor in its own right, but it's also a confounder of MI type. So first thing we do with all multivariable models is we check the overall significance of the model. Does the model work? And yes, it does. It's a highly significant model. Because if the model doesn't work, we don't need to go on to see which parts of the model worked. All right? So we do the overall model. Yes, it was significant. Now we can go and look at the individual effects. They both remain statistically significant. The hazard ratio for MI type went down a little bit. When we account for someone's BMI, the MI effect wasn't as profound. I mean, it was still a large effect. It's 1.8 times the chance of dying if you have a non-Q wave. Okay, so that's really all we need to say about that. Okay, so that's just running through a Cox regression. Personally, I think hazard ratios are much easier to interpret than an odds ratio from logistic regression, because we can talk about the probability or the chance of dying. We don't have to mess around with odds, which are horrible things. Let's face it, odds are horrible things. Okay, so now I'm just going to talk about assumptions, and I'm only going to really talk about that there are two main assumptions that Cox regression use. First, that continuous covariates have a log linear relationship with survival or whatever our outcome is. In other words, why would we use a log linear model if there wasn't a linear relationship? I'm not going to talk about that anymore. There are methods for checking this and so on, but I'm not going to go into detail about it. The second assumption, which is central to Cox proportional hazards regression, in fact, it's so central, it's part of the name. And that is that hazards remain proportional over this whole survival experience. Now, that's a horrible way of saying that if you've got twice the risk on day one, say, as a male, I have twice the risk of dying compared to a female on day one, then on day 50, I should also have twice the chance of dying. On day 100, I should also have chance of dying. In other words, the relative hazards should stay the same throughout the whole survival experience. And that's what proportionality means. In other words, a hazard ratio is an average measure of comparative risk. And we want to know, is this average representative of risk over the whole survival experience? If it's not, I should not be quoting it. So for example, if I've got twice the chance of dying on day 10, but 100 times the chance of dying on day 500, then I shouldn't say my hazard ratio is 2, because that is misrepresenting the risk. Okay, so does it fit the whole survival experience? And that's what proportionality is about. It makes a lot of sense when you think about it. Really, we're asking, is the hazard ratio a reliable statistic to represent risk, relative risk? Okay? Okay, so there are a couple of ways. There's two main ways of testing this proportionality assumption. The first is a graphical method called the log minus log plot, and the second is a method called the Schoenfeld or Schoenfeld residuals, and that is actually a formal test. Okay, I'm going to go into more detail about the first method, and I'll leave the Schoenfeld residuals, but really it's no harder to use. The reason I'm going to use this is because I think it's a relatively intuitive way. It has an advantage and a disadvantage. Okay, why is it called the log minus log survival plot? Because it is literally the log of the negative log of the survival function. Okay, so it's literally a log minus log survival function. Okay, so why does it do this horrible transform on the survival function? Simple, to make them straight lines. Okay, because if we can make the survival function straight lines, we can plot them and then see if they're parallel. Okay, so this is just a weird and wonderful transform to make the survival function a straight line, and then we can compare them. And the general rule is if the log minus log survival curves for our different groups are parallel, then we are happy. Proportionality is safe. Okay, so let me show you a plot here. This is from a totally different study, and here is the log minus log plot of 3 different groups. It's got to do with tumour extent. And we can see that while there was a difference in risk for the 3 groups, the survival curves seem to be, or I should say the log minus log of the survival curves seem to be parallel lines. So therefore a Cox regression analysis of this data is valid. Okay, it is as simple as that. The problem with this log minus log plot is that it is subjective. It's a graph, okay? What I think is proportional, a reviewer might disagree with, okay? And they might argue with me about it, all right? So we could say that it's subjective. However, its strength is that it's intuitive and we can use our eyes to do it. The problem with the Schoenfeld residuals is that it's a formal test of the assumption. Now, I do actually use this method, but I just want to make a comment. I almost never use tests of assumptions. The reason is because, particularly in clinical trials, the reason is a clinical trial is a powered study. We power it to detect a difference between groups in our endpoints. We do not power our study for the assumption tests. So for example, tests of normality are very sensitive. They're very powerful tests. So in other words, if I've got like 50 or 60 patients, my data are literally never normally distributed. Not because they're not normally distributed, but because the assumption test says that they are not. So what do I do when I look at normality? I use my eyes and I look at a histogram, okay? The within group distribution for each group. If it looks normal, it's normal enough. Okay, so that's the first point, that assumption tests are usually very overpowered or arbitrarily powered at the very least. It's got nothing to do with the power analysis we do. 2, these assumption tests are not actually linked to the robustness of the method. So for example, I might find that my data depart a little bit from normality, but that's not going to cause a problem for my t-tests. T-tests are incredibly robust tests. So my assumption might say, no, your data aren't normal, but that's not going to actually affect my results whatsoever. Okay, so really, I strongly advise people against using assumption tests. By tests, I mean things that spit p-values at you. Okay, use your eyes, look at equal variances, just look to see if they appear normal. I know you're going to have to argue with people if you do it, but using the wrong test that gives you the wrong answer is not a solution to arguing with people, okay? They're just wrong. They don't represent what people think they do, okay? However, having bitched about that, this is one I do use, okay? Simply because it's not so intuitive. This is a bit more of a complicated case, and this test was developed specifically with Cox regression in mind. Whether its power is actually, I guess, calibrated to Cox regression, I don't know. But it is one of the ones that I do actually use. I just don't use normality tests and variance equality tests. I don't use them. I use my eyes. All right. Now, I'm actually not going to run through one of these. I just want you to know about it. The other advantage of this Schoenfeld residuals method is that the log minus log plot method only works for categorical variables. Now, sometimes what you could do, if you had BMI and you're using it continuously, you could split it into 3 or 4 different groups and then just compare the proportionality of those 3 or 4 different groups. A lot of time with BMI, we use it in groups anyway. But even if it was a continuous variable, we could split it into tertiles, say 3 groups, and then just actually look at the log minus log plots for them. However, a simpler way of doing it is just use the Schoenfeld residuals, because it doesn't care whether a variable is continuous or categorical. It will test them regardless. Okay, so that's all I wanted to say about vanilla Cox proportional hazards regression and the simpler methods. Now what I want to do is just talk about the other more complicated advanced survival analysis methods. And as I said at the start of this lecture, I would dearly love to do 3 or 4 lectures just on survival analysis. It's a whole sub-discipline of biostatistics. The only problem is, you know, these sorts of analyses are relatively rare. If you come from certain areas, they're much more common. So I'm not sure if I'd get people turning up. Nevertheless, I'd love to talk about them anyway. Okay, so the first thing I'll say is that there's various extensions of Cox regression or alternatives to Cox regression that deal with a variety of problems that we might come across with our survival data. And I'm not going to be too exhaustive about this, we just don't have the time. But I will theme a couple of these advanced models in terms of the problems they solve. And that these problems might be due to the research question, or they may be due to just problems we have with the data. Now, let me give you an example. A research question might be about competing risks, or a research question might be about recurrent events. We're not just interested in something happening once, but 2 or 3 or 4 or 5 times. So if we're talking about relapse or remission or recurrent events, then our research question is about that. That's not a data problem, it's a research question problem. However, if our data are not proportional, that would be a database problem and we'd have to solve it. So I'm going to talk about 3 particular problems. Disproportionality, what should we do if we see this? Now remember, disproportionality means an average hazard ratio does not hold across the whole survival experience. So males it might be much riskier to be a male at the start than it is at the end of the survival experience. So I just want to remind you that's what disproportionality is about. Competing risk is where we have 2 or 3 or 4 possible outcomes. Now I'll leave that until we get to it. Finally, recurrent events and time-varying covariates. Now, these are not equivalent problems. They're quite different from each other, in fact, but we use the same types of models to solve both of these problems, okay? And this is really fun stuff. I actually have to say, all of these methods, they're just wonderful. I really like them. Okay, so let's talk about disproportional hazards to start with. Generally, what it sort of comes down to is difference in baseline survival. So this notion of H0 of T, that baseline hazard function, is not the same for everybody. Different groups have different baseline hazards. In fact, different patients can have different baseline hazards. Okay, so the assumption of Cox proportional hazards regression is not met. Okay. Cox regression assumes that any and all difference in patient survival can be fully explained by the covariates in the model. Beyond that, all patients come from exactly the same distribution. They share a baseline hazard function, except for those what can be explained by those covariates. This is often not the case, and for several reasons. Okay, for several reasons, and I'm going to talk about some of these. But when this is not the case, we need to account for these different subpopulations in our data, and there are 2 approaches commonly used. First, parametric survival models. So examples of these would be an exponential or a Weibull distribution survival models. I don't use these too much. I use other methods to do it, but sometimes survival takes a very distinct shape which can be represented by particular distributions, be it an exponential distribution, a Weibull distribution, or several other distributions. Now, yeah, so these are parametric. They have a particular theoretical distribution we are assuming. The other approach would be a stratified Cox regression, where we assume different baseline hazard for different subpopulations. Now, where would you do this? Basically where we have lots of differences between subgroups in our studies, and we either don't have the variables in our data, there's just too many of them, or it would just make the model way too unwieldy. We would need 30 or 40 or 50 covariates in the model to explain these differences. So often there's an identifiability issue with this. A perfect example of where this might occur is if you're in international studies and the risk profiles of the different countries are quite different. There might be cultural, genetic, blah, 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 all sorts of differences between the countries, and you just don't have those variables measured in your data set. So what you would do is you'd fit a model for, say, Australians and a model for Indonesians, which have, other quite difficult to explain differences between them. Okay, so we might use something like that. Okay, so if that would occur, what we would do is we would have a baseline hazard function for each subpopulation in our data. Now, the one thing we should say about this particular stratified Cox regression model is we assume, regardless of this baseline hazard that each subpopulation has, we assume that the covariates affect them in the same way. In other words, if Australian males have twice the risk of a myocardial infarction, Indonesian males also have twice the chance of a myocardial infarction. Okay, so in other words, we're assuming this part of the model is exactly the same for the different subpopulations, but the different subpopulations are allowed to have their own risk profile. Okay, that's that. That's all I really wanted to say about that. Okay, now the second set of models I will talk about are competing risk models, and I love these. I love them. The only reason I don't tend to use them that much is they tend to be associated with very particular clinical areas. And the area you see it the most is areas that involve transplant. Okay, so let me give you an example of where competing risk models come in. Here, this is one we did this year actually, where we considered Fabry's disease. We wanted to see the risk of patients with Fabry's disease, which is quite a rare kidney disease, and patients without Fabry's disease. And we had two possible endpoints for them. One, the patient died due to kidney disease related, for kidney disease related reasons, or they experienced graft failure, and we're just talking about graft failure, we're not talking about death due to graft failure. So the two endpoints we're interested in was basically the transplant failed or they died of their underlying disease. Okay, those would be the two outcomes. So there's two things I just want you to note about this. First, that we get a curve for each outcome for each group. So the black curves here are for the non-Fabry's patients and the red curves here are for the Fabry's patient. The solid line is for the graft failure and the dashed line is for the death, okay? So you can see in this analysis, sorry, there's one other thing I should mention. In competing risk studies, we do not use Kaplan-Meier curves. They misrepresent the survival distribution. What we go back to is this cumulative survival distribution, the one I mentioned right at the start, which is often called the cumulative incidence curve. Okay, so in other words, we can see it as something very closely related to 1 minus the Kaplan-Meier curve. It's not exactly the same, but it's very closely related to that. If it was exactly the same, we could just use the Kaplan-Meier curve. Okay, so in other words, it starts at 0 and makes its way up to 1, whereas the Kaplan-Meier curve starts at 1 and makes its way to 0. Okay? So here, and this is a very interesting example, we can see that for Fabry's patients that they had a significantly lower chance of dying from kidney disease compared to non-Fabry's patients. Have I got this right? Sorry, they had a much higher chance of graft failure. Sorry, a much lower chance of graft failure compared to non-Fabry's patients, but they had a much higher chance of dying compared to non-Fabry's patients. So in other words, the risk of the outcome changed direction depending on what outcome it was. It's worse to be a Fabry's patient if you're just talking about kidney disease mortality, and it's better to be a Fabry's patient if you are talking about, I forgot what I said, what order I said that in, sorry. It's better to be a Fabry's patient if you're talking about graft failure. Now, bear in mind here that if you die first, you've got you have zero chance of graft failure if you're already dead. So we do have to take those things into account. Okay, so I'm not going to mention anything more about that. And remember, what I'd say is if you have this type of problem, this sort of research problem, just come to us. This is sort of not the sort of thing, if you haven't done any survival analysis before, you do not start with competing risk models. They're heavy duty things. Okay. The last thing I wanted to talk about was when we have recurrent events and time-varying covariates, okay? Now, these are very different issues, okay? But they also, in some respects, are actually related to it. Now, first of all, let me define what I mean by recurrence, okay? We can see recurrence as repeated values of the outcome, okay? So that might be relapse, but, and this is a maternity hospital, it might be a childbirth event for a mother. So a mother might have 3 or 4 or 5 or 6 children over her life, and a childbirth would be a recurrent event for that woman, okay? And if we wanted to analyse that, we would need special models. If we wanted to take it, we could say, well, time to first child or time to second child, we could be very, very specific, or we could just actually model the recurrent events themselves. The second case is time-varying covariates, which we can see as repeated values of the predictor. So we might measure systolic blood pressure at baseline, day 5, day 10, etc. So that's the difference. One is a repeated measure of the outcome for a time to event outcome, and one is a repeated measure of the predictor. However, in both of these cases, we have clustered data. We have repeated values that can be linked to a particular patient. So we will often use similar types of models to deal with these very different problems. And in both cases, we can use frailty models or its friends, its more recent friends, okay? To deal with the data clustering that these sorts of designs actually result in. Okay, so I'm just going to mention this about frailty models and then we're done. So frailty models is a relatively simple, in fact, it was the first mixed model that was actually used in survival analysis, and it sort of relates to the other mixed models we see, linear mixed models and generalized linear mixed models. There are both Cox regression and parametric model versions of the frailty models. How they work is by including a multiplicative random effect, which we call the patient's frailty, to the model, and this random effect remains latent. In other words, we don't really want to model patient frailty, we just want to account for differences in patient frailty. Now, I should probably mention that, and by the way, these models were first used quite a long time ago. And I remember in the first paper it was ever used, they talked about accident proneness, which is a horrible way of saying it, but accident proneness in elderly people, and I think it had to do with hip fractures or something like that. So what they were saying is that different people have different risk or accident proneness that can't be explained by the variables we measured in the models. Now, this is very similar to our first problem, that we have subpopulations in our data. The difference here is that every patient represents their own subpopulation. Okay? Also, since the frailty model came out quite a long time ago, there have actually been advances. Now we have things like Cox mixed models, because the frailty models are rather simplistic mixed model. And now with Cox mixed models, we can actually analyze more complex multi-level designs. So we might have recurrent events and time-varying covariates in a multi-center study. So there might be multiple levels of data clustering, and we can represent this using Cox mixed models. As I said, I'm a little bit frustrated because I would have loved to have gone through an example of these more advanced things, but we've just run out of time. Okay, that's that. Thank you very much.